Okay, great. So, yeah, lovely to see you all. I really hope you're doing well. Um, so, welcome to this second lecture on natural deduction for truth functional logic. The aim for today is actually fairly straightforward. I want to get through some proof theoretic notions. And really what these are is roughly parallel to some of the semantic properties or semantic notions we defined with truth tables. But importantly, these are all going to be defined in terms of our proof theoretic system, this natural deduction system that we set up. Then I want to talk quickly about some proof strategies. We talked about these in the tutorials, but these are really broad, general ways to kind of get natural deduction proofs going. How might you build them? And that will take us to the break, at which point we'll pause, we'll come back, and we'll do some practice proofs. So that's the plan for today. Let's go ahead and dive into the proof theoretic notions. So I'm going to presuppose that we have some grip on most of the rules, but again, we'll talk a little bit about those in the second half again. So the first thing to note is much like we could with our truth tables or with interpretations, right? With those, we defined a double turnstile. With our natural deduction system, we can define a thing that we'll call the single turnstile. And shockingly, right, the double turnstile had two kind of things going off the vertical line. This one only has one. So the single turnstile concerns, we can call it provability, or is provable from, or there is a proof that, da-da-da-da-da. It's only about the construction or the possibility of a construction of a natural deduction proof. So the single turnstile, again, is something like provability. It is similar to, though essentially distinct from, the double turnstile. Right? So the double one, that had something to do, when we're thinking about TFL, with the existence of valuations. Right? Assignments of truth values to atomic sentences. Or, in terms of our machinery, things on a truth table. Right? Rows, often, or a combination of rows on a truth table. So that was what the double turnstile was about. The single turnstile is just, hey, is there a proof that we could make? Now, of course, what we can do, as soon as we have this single turnstile, is we can put it to a bunch of uses. So we can say something like this, right? We'll have, again, note it's in my sexy swash font, so this could be any sentences we like. A1 through AN, single turnstile C. This is another way of saying there is some proof, or it's possible to prove, right? Taking A1 through AN as our assumptions, C. So that is, we can take the stuff on the left as premises, as assumptions for our natural deduction, and we can end the proof with sentence C. And much like with the double turnstile, to give the fancy name, this symbol is variably polyadic. What that means is it can take any number of sentences on the left, but it always only has one sentence on the right. There's always just one sentence as the conclusion. There can be anywhere from 0 to, theoretically, an infinite number of premises we're going to take. So again, this is basically another way for us to say you can construct a proof that takes these as premises and has this as its conclusion. And of course, we can also do this, right? So we can draw the line through the single turnstile. And this is just to say there is no such proof. There is no proof that starts with these assumptions and ends with C. So again, this is kind of familiar to the notion of tautological entailment, but instead of entailment, what we're talking about is provability. So once we have this single turnstile, we can put it to use and define up a bunch of notions. The first notion we'll define is the idea of being a theorem. We can say that a sentence A is a theorem if and only if there's a proof of A that starts with no assumptions whatsoever. That sounds kind of crazy, but again, the idea is It's a theorem if we can literally bootstrap it from nothing. We can prove it from no assumptions at all. Now, showing that a sentence is a theorem is reasonably straightforward. What we do is we literally construct a proof that ends with that sentence. But importantly, we start with nothing above our assumption line. So a proof for a theorem will look different than all the ones we've done before, in that the very first step, the first numbered line, will be below the assumption line. So that's what we do when we prove that a sentence is a theorem. We'll go through an example in just a moment, but again, I want to give you the basic idea. Right? So showing a sentence is a theorem, you show that you can literally derive it from nothing. You can prove it with no starting assumptions whatsoever. You don't need any help to show that it's true. Now, this idea, being a theorem, what is it very similar to? Yeah, so it's very similar to a necessary truth, right? And importantly, so on those same lines, what was the notion for TFL? Right? There was a special term that we called sentences of TFL that were necessary truths. Do we remember? Tautology, right? It's a tautology. This is the proof theoretic version of a tautology. Just like tautologies could be derived from anything, because they're always true, so there's no way to make premises true and conclusion false. Theorems can be derived from anything. They can be proved from anything at all, because they can be proved from nothing. Now, weirdly, it's easy, in a way, to show a sentence is a theorem. It is extremely difficult to show that a sentence is not a theorem. Because doing this would require us being able to show that it is not possible to construct a proof. You have to think about every possible proof that you could build. So this is a kind of interesting thing here, right? Our natural deduction system can show you that a sentence is a theorem, but it weirdly struggles to show you that a sentence is not. So there's our first notion, being a theorem. You can prove it from nothing. So here's just a slightly silly example. We're going to show that it's not the case that A conjunction A. We don't need any assumptions. We draw our assumption line at the top, and our first numbered sentence is actually going to be a sentence in a subproof. And then we go through and we show, hey, this sentence leads to a contradiction, so it must be false. It's being true leads to bad things, so we can do negation introduction. And note that this proof doesn't require anything up here. So this shows that that sentence at the bottom, the sentence at line 5, is a theorem. Okay. This is a proof, if you like, of what's often called the law of non-contradiction. That is, for no sentence A and its negation are both true. So one thing to note, and we'll talk more about this in tutorials and things, one thing to note, when you're doing theorem proving, 99% of the time, your first step for proving something is a theorem is going to be opening a subproof. Since you start with nothing, you're going to have to give yourself something to work with. It's not always. There's one small exception. We'll talk about that when we get to it. It's only an FOL. Okay, so that's one thing we can do. We can show that sentences are theorems. Another thing we can do, we can show that two sentences are what we'll call provably equivalent. So we can say that two sentences A and B are provably equivalent if and only if each can be proved from the other. That is, we can build a proof that starts with A and ends in B, and we can build a second proof that starts with B and ends with A. It's sort of showing a biconditional, right? But in a much bigger way. Right? We're literally constructing two separate proofs. So provable equivalence is very similar to another notion that we had, a semantic notion, right? Tautological equivalence. Right? Tautological equivalence was when sentences always had the same truth value. Provable equivalence is structurally similar. It's if you have one, you can get to the other, and vice versa. So, to show that two sentences are provably equivalent, what we do is we build two proofs. Right? One that starts with A and ends in B, one that starts with B, ends in A. Weirdly, it's relatively easy with our natural deduction system to show that two sentences are provably equivalent. It's very difficult to show that they are not. And the reason here is what we have to do is show that there is literally no possible proof that gets us from one to the other and vice versa. And again, that's kind of weird. But it's worth flagging up. So, again, to give you an example, right, here's a sort of provable equivalence pair of proofs. Slightly silly, but it's nice, right? We have two sentences, G, and then we have not G. And we can show that these are provably equivalent. First, we go from left to right. So we start with G, and we eventually end up with our quadruply negated G. And then we can go the other way. And the other way is very easy. You just do double negation elimination twice. But importantly, when we're showing that sentences are provably equivalent, to answer the question, you've got to give me two proofs. That's why they're worth twice as much points. Okay. So again, we've got proving a sentence is a theorem. We have proving that sentences are provably equivalent. Here's a third notion we can show. We can show that some sentences are what we'll call jointly contrary. So sentences A1 through AN are jointly contrary if and only if we can take them as assumptions and derive a contradiction. Now, notably, in order to do this, what we have to do is actually generate the contradiction on our main proof line. The upside down T needs to be on this line, not in any subproof. We need to make sure it's on the main proof line. Because what we're trying to show is that were these sentences all true together, bad stuff. It's basically a version of doing something like negation introduction, but all we're saying is these sentences can't all be true together. So to show that some sentences are jointly contrary, we take them as our assumptions, we do whatever we need to do, and we end our proof with an upside down T. And again, joint contrariness should sound or should kind of set off alarm bells. It's very structurally similar to another semantic notion we talked about, right? It's very similar to joint tautological inconsistency. Remember, in that case, that was showing that there was no valuation where all the sentences are true together. Here, what we do is we show if they're all true, you get a contradiction. It's the same kind of idea, we're just coming at it with different machinery. And much like the other ones, it's relatively easy to show that some sentences are jointly contrary. We just build our proof. It's really hard to show that they're not. Because this requires thinking about every possible proof that one could construct. And our machinery, our natural deduction machinery, is just not set up to be able to do that kind of thing. So far, so good. Right? We have proving a theorem, we have proving provable equivalence, and we have proving being jointly contrary. And a slightly silly example, but here you go, right? Here's three sentences, and we can show that they're jointly contrary very quickly, right? From 1 and 2, we can derive B, which of course immediately contradicts with sentence 3. Note, we could have done this a different way too, right? We could have used B and 2 to derive not A through modus tollens, which would have then conflicted with sentence 1. All we care about, though, is just getting this sweet upside down T at the bottom. Okay. So before we go on, pause. Do we have a feeling? Do we kind of get what we're after with these 3 concepts? So again, being a theorem is roughly similar to tracking tautologies. Right? Provable equivalence is very much like tautological equivalence. And joint contrariness is very similar to tautological inconsistency. But importantly, in these cases, they're defined in terms of the different machinery. In every one of the things we're talking about now, we're always defining it in terms of our natural deduction systems. What can our proof system show us? And notably, again, our natural deduction system can show very easily a sentence is a theorem, that 2 sentences are equivalent, or that some sentences are jointly contrary. But by itself, it cannot show that they are not these things. It's not set up for that. So that's something to note. Now for TFL, of course, we know exactly what tool we would use for all of these cases. If you wanted to show that a sentence isn't a theorem, that is, if you wanted to show it wasn't a tautology, how would you do it? Well, you build a table, right? You give me a valuation where it's false. It's easy. For TFL, this is not that exciting. But where this is going to come in to the money is when we think about FOL. Because you'll note the gaps here, when we think about first order logic, perfectly correspond to what interpretations could do. So when we think about FOL natural deduction, it's going to be able to do all of this stuff and not this. But when we think about interpretations, interpretations could do all of these, but not these. That's why the 2 match perfectly together. So it's worth noting, all of this hinges on something very, very, very deeply important. When we talk about the single turnstile, and we say something like this, again, we're talking about provability. This tells us there is some proof, or it's possible to construct a proof that takes A1 through AN and ends in C. And this tells us, when we're thinking about TFL, that there's no valuation that makes A1 through AN true and ends in C. Sorry, that ends in C being false. These look structurally similar, and they are structurally similar. But importantly, they are structurally similar. They are different notions. This is about valuations. The double turnstile is about valuations. This is about proofs. They're different. That's the most important kind of underlying conceptual point to make. But here's the really cool thing. While they are different, they are extensionally equivalent. That is, whenever provability holds, entailment also holds, and vice versa. While provability and entailment are different notions, they're defined in terms of different machinery, right? One's basically in terms of tables, one is in terms of our natural deduction system, they line up. And because they line up, this means that we can use either tool whenever we want to. So we can say that an argument is valid if and only if the conclusion can be proved from the premises, if and only if there's no valuation where all the premises are true and the conclusion's false. All of these notions should line up. Similarly, we can say 2 sentences are logically equivalent or tautologically equivalent if and only if they're provably equivalent. Provable equivalence and tautological equivalence line up. And then another nice pair. Some sentences are jointly consistent. That means it's possible to make them all true together, jointly tautologically consistent, if and only if they're not jointly contrary, and vice versa. So to go back a little bit, this tells us how to do this, right? If we can give a valuation that makes them all true, we've explained why it wasn't possible to build this proof. Another neat thing, in fact, I've already sort of given it away, right? A sentence is a tautology if and only if it's a theorem, and vice versa. Being a theorem and being a tautology line up perfectly. Now again, for TFL, this isn't that shocking a revelation. For FOL, though, this makes all the difference in the world. Because it means that all of that stuff we couldn't do before, once we get our FOL system going, we'll be able to do it. Remember, for example, when we were doing interpretations, you couldn't show me that an argument in FOL was in fact valid. All you could do was construct a model to show it's invalid. Now you have the tool, or you will, very shortly, the tool to show me when it's valid. You build a proof. So again, to stress, while the single and double turnstiles agree, they are extensionally equivalent, they remain different conceptual notions. One's about provability, one's about valuations in this case, if we're thinking about TFL. Okay. So that was the big kind of content for this lecture. I wanted to give you these notions. Now, obviously, one of the things I will do is I'll ask you to use the natural deduction system to track some of these proof theoretic notions, right? Syntactic properties. So I'll give you 2 sentences and ask for you to show me that they're provably equivalent. Right? And we'll go through an example of that after the break. But before we get to that, I want to talk very quickly about proof strategies. So obviously a huge part of what we're doing here is building natural deduction proofs. And that's hard, I'm not gonna lie, right? Again, especially if you've never done anything like this before, it's weird. And often the hardest part is to have any concept of how to start. How to get this going. It's cool to be able to like list the sentences and draw the assumption line and everything, but then it's just like, okay, what the hell do I do now? So I want to mention 4 kind of broad things to keep in mind as you're doing these natural deduction proofs. So the first thing to say here is unfortunately, there is no simple mechanical recipe for generating good proofs. It's not like building a table. But there's still some useful suggestions or strategies to keep in mind. The first one is one that we've done quite a bit if you've been to the tutorials, right? This is one I'm a very strong advocate of. And the idea is that a good way to get going is to work backwards. So if you're going to build a natural deduction proof, start off by writing the assumptions down, getting everything going, and then put the proof aside and think about what's the last step in the proof going to look like? What's the last rule that you will use? And a big clue, something you can use to help yourself here, is if the conclusion has an operator, think about using the introduction rule for that operator. Then, literally, just work backwards. Say, okay, if I use this rule for the final step, then this will have to have happened before. So then the previous step before that, what rule would I have used to get it? Okay, cool, probably this one. And then we just go step by step, working backwards until we've either gotten all the way back to the assumptions or we have a general idea about what the proof's going to look like. Plan your moves before you just start jumping into the proof. And one good place to start your plan is at the end, because you know where you have to end up. So that's one, work backwards. The second little bit of advice or suggestion I can give you, ironically, is work forwards. That is, work with what you've been given. When you start a proof, you will often, unless you're proving something as a theorem, be given a bunch of sentences. So one of the very first things you can do is ask yourself, well, looking at the assumptions I have, what are their main operators? What connectives do they have? What steps or rules can I immediately apply? What can I get out? So if you have a sentence that's got a conjunction, cool, let's think about conjunction elimination. Is that going to help me get to anything that I want? Ooh, do I have a conditional and an antecedent? Is that consequent going to help me out? Do I have a conditional and a negated consequent? Awesome, I can get the negated antecedent. Again, think about what initial operations you can make. What sort of stuff can you go ahead and produce? Is this going to be at all useful? This is particularly useful when you pair it with the previous strategy. That is, start by thinking about the last step to give you, okay, the big move in this proof is going to be negation introduction, if, say, the sentence you have at the end has a negation. Then you can go back and say, all right, with that in mind, how am I going to generate my negation? What stuff can I manipulate from my initial assumptions? Again, these two go hand in hand very nicely. The third kind of broad suggestion I can give you has to do with something we haven't really done yet. But this is actually a proof type. And this is a proof indirect. So to put in proper English, an indirect proof. There we go. That's the word I was looking for. Right. And the idea here, to prove something indirectly, is you prove that its negation must be false. That is, you want to get to some sentence. In order to show that some sentence is true, you give a subproof that starts with the negation of what you want to get to. So let's say we want to eventually get to sentence P. To prove it indirectly, what we would do is we would start a subproof with not P. And the aim here is to eventually show that not P leads to a contradiction. That is, hey, not P must be false. What this lets you do, having shown that not P is false, is you can then do negation introduction. Hey, if not P is false, then it's not the case that not P. And then your final move, your last step, is double negation elimination. It's basically just a way to say, hey, if not P is false, then you know what has to be true? P. So it's an indirect proof, because instead of actually directly showing some result, you show that its opposite must fail. This is an extremely useful trick if you are absolutely stuck. If you've done the previous two and you cannot think of any way to make the stuff working backwards work, or to figure out how to go from where you started, think about doing proof by indirect. So these are three general strategies. The fourth strategy isn't so much a strategy, just as a bit of advice, which is just don't give up. Right? Endure. Right? If things aren't working, try something different. Right? If you've made a little plan and it's just not really working, cool, scratch it off, start again. Right? Don't give up, basically. Right? This is hard. It's difficult, again. There's a lot of different moving parts here. But it's also really fun. It's amazingly satisfying when you suddenly just like, oh crap, it goes like this. Oh, yes, it's beautiful. It's so much fun when it works. And pushing through is actually part of the fun of it. It's like a really good puzzle. When you figure out the solution, it's very satisfying. So that's the kind of proof strategies. Again, to stress, in all of these cases, there isn't any cold, mechanical way to guarantee a good proof. It's just not how these things work. It isn't like with a truth table, where they were guaranteed to build a good table if you follow these steps. But we can come pretty close. Again, this sort of working backwards gives you a way to start planning. This sort of working with what you've been given is another way to start planning. If you can find a way to make those two meet, you're in the money. Okay. So that's really what I wanted to cover today, lecture-wise, right? Is again, just introducing you to these proof theoretic notions, these concepts that we can use our natural deduction system to track. And in fact, that's what we're going to be doing, right? For things like the final exam, I'll give you 2 sentences and ask you to show me that they're provably equivalent. Or I'll give you a sentence and ask for you to show me that it is a theorem. These kinds of things. So what I want to do is we'll take our break in just a second. And we'll come back and we'll do, here as a big group, at least one of each type. So we can kind of see what it looks like and get a feel for how these sorts of proofs and using natural deduction to track proof theoretic notions go. The last thing I want to say before we go is, of course, what we've done, right? TFL natural deduction. Right? So nicely done. We've learned it. Excellently done. This is a stepping stone, because what we really want to get to is FOL natural deduction. Because this is where we need it. Right? FOL natural deduction, we need to have this system because interpretations were a flawed tool. They only let us do half of the things we want. Well, unsurprisingly, FOL natural deduction is also a flawed tool in the sense that it only lets us do half of what we want. But praise Jesus, the two halves perfectly mirror each other. So we've learned TFL natural deduction. We started walking so we can run. We're going to work on FOL natural deduction for the next 2 weeks. This will be the rest of what we do. So what I would suggest, again, is very strongly suggest, have a read through the chapter for next week. Again, we're going to get some more rules for the natural deduction system for FOL. Everything we have learned for TFL also works for FOL. All we're going to get is rules for the quantifiers and for identity. So there's not going to be much new stuff, but there'll be a few more rules. But of course, in order to do this, to do natural deduction for FOL, we've got to be able to do natural deduction for TFL. And the last thing before we again take our break, final thing, is much like before with the midterm. I appreciate that some people see first order logic and then just immediately kind of like, ah! So when it comes to the final exam, you can do just fine if you only know how to do TFL natural deduction. Right? The proportion of points is going to be broadly the same. Right? Again, that's by design. You're welcome. Right? So, but importantly, I really want you to learn this because I think this is super cool. So what we're going to do, we'll take a 10-minute break. It's 24, effectively. So we'll take a break. Well, we'll go to 45, 35. That was what I wanted, 35. So 11 minutes. If anybody wants to stay to work on the practice proofs, you're very welcome. But also, I'm going to record it, so I won't be terribly offended if people don't stay. Thank you guys for coming. And yeah, we'll see you all. Ooh, and again, reminder, no tutorials this Thursday and Friday. They've been moved to next Monday and Tuesday.